So now we will do examples on integration over a closed path. So find the work done. Find the work done by the force F in moving a particle around a circle C in in the XY plane with center at origin and radius 2. Now, where F excuse me, where F is x plus y plus z times I cap plus 2x plus y times j cap plus 2x minus y plus z times k cap. This is the question. So we have to find the work done. So work done is a scalar quantity. We get F dot dr. F dot dr integrated along C. Now I am putting this circle like this because it is a closed loop around a circle. So work done is this. Now F is this. What is dr? So R, in our case, because it's an xy plane, R is xi plus yj and z is 0 because it's the xy plane. And now dr will be dx plus dy, dxi plus dyj. Now we have to integrate around the circle. Okay. So there's the origin and radius 2. Now any point P on this circle, this OP is this vector R. This is x comma y. Now this will be 2 cos theta, 2 sin theta. We can write in terms of polar coordinates. The reason is we have to integrate around the circle. What remains constant is the radius. What changes is the angle. So the same thing we can write as cos theta sin theta. So now x. So around the integral, we are around the circle we are integrating. So put x is equal to 2 cos theta, y is equal to 2 sin theta. So dx is minus 2 sin theta d theta, and dy is 2 cos theta d theta. Okay. Now, second thing, because we are integrating along this of course it's a three-dimensional function, vector function. But because we are integrating around this circle, okay. So around this circle we are integrating. So around that circle, x can be written as 2 cos theta, y can be written as 2 sin theta, and z will be 0. Otherwise, we cannot write that way. Okay. So in any case, what we get when we take f dot dr, we will simplify now. F dot dr, we will get, see, this is dr and this is f. So f dot dr will be x plus y plus z dx plus 2x plus y dy. Now, when we are integrating around the circle, this is the work done. Then it will be like this: x plus y plus z dx plus 2x plus y dy. Now, to get to a common integral, a common limit of integration and so on, we can substitute x is equal to 2 cos theta, y is 2 sin theta, z is 0, times dx is minus 2 sin theta d theta plus 2 into 2 cos theta, that is 4 cos theta, 2x is 4 cos theta plus 2 sin theta times dy 2 cos theta d theta. Now the limits of integration, now we'll apply theta equal to 0 to 2 pi around the full circle. So now we can take d theta common. This will be minus 4 cos theta sin theta minus 4 sin square theta plus 8 cos square theta plus 4 sin theta cos theta. So what happens is this and this cancels. So now we have the square term. So we get 2 pi minus theta. If we substitute, you will get the same function. Sine square of 2 pi minus theta will be sine square theta. Cos square of 2 pi minus theta will also be cos square theta. So because of this, using the property, we can reduce to 0 to pi. 0 to pi. 8 cos square theta minus 4 sin square theta d theta. Further, we can simplify. Because again, pi minus theta, cos of pi minus theta is minus cos theta, but when you do square, you get the same quantity. Sine of pi minus theta is sin theta. So again, we do integral 0 to pi by 2, 8 cos square theta minus 4 sine square theta. Now, integral 0 to pi by 2 cos square theta, if it is I, it is same as integral 0 to pi by 2 cos of pi by 2 minus theta. That will be sine square theta. Okay, integral 0 to a f of x dx is same as integral 0 to a f of a minus x dx. So when we do that, we get this. And I plus I is integral 0 to pi by 2 cos square theta plus sine square theta. It is 1. So integral 1 d theta is theta. From 0 to pi by 2, you get pi by 2. So I is pi by 2 upon 2, which is pi by 4. So that's what, so both cos square theta and sine square theta integral from 0 to pi by 2 is pi by 4. So this is 4 into 8 times pi by 4 minus 4 times pi by 4. So we get 2 pi minus pi is pi. So we get the answer as 4 pi. This is the integral. So it was easy. It was not a difficult concept. F is given, circle is given. Now f dot dr we have to do around the circle. So dr is dx dy. We took the help of polar coordinates. So x is 2 cos theta, y is 2 sin theta. We substituted that in f dot dr. And we just did the integral around the circle from theta is 0 to 2 pi for a circle. So this is how we do it. Yeah, there's another important example. I hope this is clear to you and you have copied now. Can I proceed further?
Yes, sir.
Yes, sir.
Now, this is a line integral. Evaluate integral around the closed loop x cube dy plus y square dx. So f dot dr will turn out to be like this. Directly it's given where C is the boundary of the triangle whose vertices are zero comma 0, 1 comma 0 and 0 comma 1. Okay. Yeah. So this is the triangle. This is the triangle. Let's say this is O, 0 comma 0. This is A, 1 comma 0. And this is B, 0 comma 1. So when we have to do a loop like this, integral C, given this x cube dy plus y cube dx, y square dx, this will be integral along OA, okay, integral along OA x cube dy plus y square dx. We will simplify this and see later. Next, plus integral AB, or we can also write OA is better because from O to A, it should not sound here. There should be numerical values. So that's why. Now A to B, we'll write x cube dy plus y square dx plus integral B to O x cube dy plus y square dx. So this is sum of three integrals. So we will take, so evaluating I1 along OA. So along OA, what is constant? What is constant? The y coordinate is constant. Y is equal to 0, constant throughout. Only x is changing, and x lies between 0 and 1. So we get y is 0, dy will also be 0. Therefore, I1 is integral OA x cube dy plus y square dx. So now what we get is, this is integral x cube dy plus x equal to, so this y will vary from 0 to 0. So there is no point. And this is 0 to 1 x y square dx. However, this will be 0. 0 to 0 will anyway be 0 with respect to y. X cube, x may exist, but dy is 0. Now 0 to 1, y is 0. Y is 0 in this term, dy is 0 in this term. So we get 0 plus 0 equal to 0. So I1 is 0. So evaluation of this integral along OA is 0. This is done. Next, AB. So evaluating I2 along AB. So along AB, equation of AB is x plus y equal to 1. Equation of AB, because it's a straight line having the intercepts on the x-axis and y-axis as 1. So x by a plus y by b equal to 1. So x by 1 plus y by 1 equal to 1. So equation of AB is x plus y equal to 1. Now this gives dx plus dy is equal to 0, which means dy is equal to minus dx, or dx is equal to dy. So minus dy. This we can use. So now let us evaluate. I2 is integral AB x cube dy plus y square dx. So let us convert everything in terms of x. So x cube times dy is minus dx plus y can be written as 1 minus x the whole square from here dx. And x ranges from, at a the value of x is 1, at b the value of x is 0. So from 1 to 0, from 1 to 0. So let's evaluate 1 to 0 minus x cube plus x square minus 2x plus 1 dx. Interchange the limit 0 to 1, x cube minus x square plus 2x minus 1 dx. Okay. So this will be x power 4 upon 4 minus x cube upon 3 plus x square minus x from 0 to 1. So we get 1 upon 4 minus 1 upon 3 plus 1 minus 1 minus of zeros. So this is 0. This is 3 minus 4 is minus 1 by 12. Minus 1 upon 12. I2 is minus 1 upon 12. Now let's try I3. So evaluating along BO, from B to O. Evaluating I3 from B to O. So along BO, x is equal to 0, which implies dx is also equal to 0. Only y changes. So I3 will be integral BO x cube dy plus y square dx. Now y varies from 1 to 0. So we get integral x is 0 times dy plus y may be there, but dx is 0. Y varies from 1 to 0. Okay. So again, we get this is 0 plus 0 equal to 0. Therefore, I integral is I1 plus I2 plus I3, which is 0 minus 1 by 12 plus 0, which is minus 1 by 12. This is the answer. Okay, this is the way to evaluate the integral along a closed loop. So first case was a circle. It was easy. We can just use a parametric form, use the parameter theta and solve. The next case was a triangle. So we need to consider the equation of triangle and see what is the integral given, and accordingly we need to evaluate. These are very, very common problems, line integral problems in GATE. So it is very important that we practice these. All right, next we will discuss surface integrals and volume integrals. So this was line integrals. Next is the surface integral. Hmm. So let S be a two-sided surface. So let one side be positive, that is the outer surface. This is outer surface of a closed shell is positive. Okay. Now let F bar be a vector which should be integrated around the surface. Okay. Consider an elemental an element of area ds on the surface whose unit normal in the positive direction, the outward direction, is n cap. Thus, now that surface can be written as an area vector ds n cap. Okay. Now, so the surface integral, so then the integral double integral we write as f dot ds, which is f dot n times ds over s, is called as the surface integral. So some function has to be integrated over the surface, like it is usually so. This kind of an integral comes, surface integral, when you have to calculate the flux, electrical flux over a surface. Or sometimes, the volume of fluid flow out of a small finite cubical volume, so suppose it's a velocity function. What is the outflow? For that, we use the surface integral. What is the volume outflow of a fluid from a closed box? So we use surface integrals for that. So this surface integral, note, integral s, when I'm writing, need not write double integral each time. When I'm writing s, it means it is a surface integral. Okay. So if needed, safe side, you don't want to get confused, you can write like this. Now this integral is also called as flux of f over s over the entire surface. Now, if, very important, when flux of f over every closed surface in the region is 0, then F bar is a solenoidal or solenoidal vector function. Okay. F dot ds over the entire surface is 0. Then it's a solenoidal function, and at any point, across any point you see, so it is a conservative field. No, for divergence, we call this as a solenoidal function. All right. Now, other types of surface integrals, which we don't use so often, is, of course, a scalar quantity over the surface, or a scalar quantity over the vector surface, and a vector quantity, instead of dotting, crossing over, we cross with the surface. So are other forms of surface integral. Next is volume integral. So this is surface integral. It's simple. F dot ds we can write as F dot n times ds over the entire surface. The question is how to evaluate. All right. So we will complete volume integrals also and then see how to evaluate. So volume integral. So integral volume means triple. Integral of f with respect to volume is called the volume integral of f on v. Now something interesting, for surface integral we could do a vector. Your differential was on the vector ds, but for line integral it is dr. Okay, what does dr represent? If we remember, dr represents, anybody remembers what dr represents in a line integral? Forgot? Let us go back again to basic vector differentiation. What did dr represent? Dr represents tangent, a tangential direction. So dr will be tangential. See, this is dr. Dr is r bar of t plus delta t plus r bar of t. So this PQ is, now when dr is very small, so it's a tangent. So line integral is like you are integrating along that line. So when you are doing a dot, f dot dr, you are doing with the tangent, dot product with the tangent of that curve. Function dotted with the tangent at every point on the curve. That is the idea. Now, when we do dot ds, interestingly, now ds depends on what direction you're going. Again, it represents a tangential plane to the surface. To the surface, it is a tangent, of course, in which over, so you are integrating each time that way. So remember, ds is a area vector. a small sample area. However, when we come to volume integral, dV is not a vector. Change in volume is not a vector quantity. It is just a scalar quantity. So we need to remember this. And dV will be taken as dx, dy, dz. This will be dV. So now if f is f of r, f of r is a function f I cap g j cap plus h k cap. Then the volume integral of f, all right, dv over the volume will be I cap times f dx dy dz plus j cap times g dx dy dz plus k cap times h dx dy dz. So this integral is a vector integral. Finally, it is a vector integral. So let's do some problems. So let's take the first one. Evaluate integral s f dot n ds, where f is equal to x plus y square times I cap minus 2x j cap plus 2yz k cap, and S is the plane, is the surface of the plane two x plus y plus z is equal to 6 in the first octant. Okay. This is just a second. Surface I have written wrong. This is 2x plus y plus 2z. Okay, this is the surface. Now this is a plane. Okay, this is a plane, and we need to integrate along this plane. Let's take the positive part. This is x, this is y, and this is the positive z. So positive octant will be this side, x, y, z. Now the plane, let us see the plane. This is 2x plus y plus 2z is equal to 6. Divide by 6. Throughout, you will get x by 3 plus y by 6 plus z by 3 is equal to 1. So in this octant, you see x, O is the origin. Now this is at x, we have 3 comma 0. At y, we have 0 comma 6. This is 3 comma 0 comma 0. This is 0 comma 6 comma 0. And we have 0 comma 0 comma 3. So let us call these points A, B, and C, these 3 points. Now, this is the plane about which we will be integrating. Okay. So these are the points A, B, C. Now about this plane along this particular surface, we'll be integrating. Now the normal to this surface by a little bit of coordinate geometry here. Remember the equation of a plane in vectors is like this: r dot n equal to p. N represents the unit normal to the surface. Okay. Equation of a plane will always be r dot n is equal to p from the origin. So the normal to this plane, how can you find, is like this. You divide by, you use the direction cosines, you divide throughout by 2x plus y plus 2z, divide by 2 square plus 1 square plus 2 square, the coefficients, both sides. Now 2 square plus 1 square plus 2 square is 9, under root 9 is 3. So we have 2x plus y plus 2z upon 3 is equal to 6 upon 3 is 2. So n cap, unit normal, normal to the plane, unit normal to the plane is this one, 2 by 3i or 2i plus j plus 2k upon 3. It will be the coefficients because r dot n, r is xi plus yj plus zk. Now n is 2 by 3 I plus 1 by 3 j plus 2 by 3 k. Okay, the coefficients. So now given f, now dot n cap ds we have to do. Okay, now n is constant, so that is not an issue, but however we need to convert. So let us first do one by one. F dot n cap. So f was x plus y square times I minus 2x times j plus 2yz times k dot n cap 2I plus j plus 2k upon 3. All right. So this will be 2 by 3 times x plus y square minus 2 by 3 times x, 2x into 1 by 3 minus 2x into 1 by 3. So minus 2x by 3 plus 4 by 3 times yz. 4 by 3 times yz. So we can simplify this and see what it is. 2x upon 3 plus 2 by 3 y square minus 2x upon 3 plus 4 by 3 yz. So 2x upon 3, 2x upon 3 cancels. So we have 2 by 3 y square minus plus 4 by 3 yz. This is f dot n. Okay. This is f dot n. Now we need to integrate along this plane now. So we have to convert ds to dx dy. So all right. So now see the conversion now. Okay. Now see, to make it easy, the conversion, I can take the projection of this along the xy plane and integrate. I want to integrate ds on ds dot n. I will convert to xy plane. It will be easier. So look at this one. Converting ds to dx dy. What is dx dy? This o xy, no? OAB. OAB in xy plane. All right. So I'm taking the projection of this entire shaded area on the xy plane. That will be OAB. Okay. So converting ds to this. So I have to dot it to convert that area. I have to dot this s ds with k. So ds dot k will give me dx dy. So ds is n cap dot k is dx dy. So now we know n cap. What is n cap? 2i plus j plus 2k upon 3 dot k. So we get 2 upon 3 n cap ds. All right, ds I'm taking off. So 2 upon 3 ds is dx dy, because ds bar is n cap times ds. So using that, we did this. So from here we get ds as 3 upon 2 dx dy. So the same ds, the integrating, I can do it over a plane much more easily, xy plane. So So I have to do this integral f dot n ds. So now let us proceed now. So we did f dot n, we got this value, this expression, and now ds we got as 3 by 2 dx dy. So from these two, integral over the surface f dot n ds is integral 2 by 3 y square plus 4 by 3 yz into 3 by 2 dx dy. Now over which surface? This will be in xy plane OAB. About this surface OAB. Now in this, everything is in terms of x and y. Only problem is with z. Now we know. Now substitute z using 2x plus y plus 2z equal to 6. So which implies z is 6 minus 2x minus 2y upon 2. This is z. So this is 3 minus x minus y upon 2. This is z. So let us first substitute that and see. So now it's a double integral. Now we have to use the concept of integration using multiple integrals, what we learned in functions of several variables. So we get 2 by 3 y square into 3 by 2 dx dy. Okay, I'll simplify fully. Plus 4 by 3 yz. So y times z. Z will now be 3 minus x minus y by 2 times 3 by 2 times dx dy. I'm still writing this as OAB. Now let us see. Multiply throughout. Let us see what we get. This 4 by 3y minus y by 2. We'll get minus 2y square by 3. And plus 2y square by 3 gets cancelled. Then we are left with 4y minus 4 by 3 xy times 3 upon 2 dx dy. All right, so multiply throughout by 3 and divide by 2. So 2 comes out common, and multiplying throughout by y I can take common. Okay, 2y comes out common, and I will get here 3 minus x dx dy. Now I have to substitute the limits. Very important. Now I'll put the limits. Now look at this figure. Look at OAB. In OAB, your z value will be 0. So then this particular region OAB, you put z equal to 0. Then 2x plus y is equal to 6. In xy plane, z is equal to 0. Therefore, we get on the xy plane, we get 2x plus y is equal to 6. So here y can be written as 6 minus 2x. So now when we do double integral, first let us integrate with respect to y. Y will start from 0 because positive octant. Y will start from 0. That means any strip. This is in xy plane I am taking from 0 to 6 minus 2x, whatever it is. Yeah, 6 minus 2x. Y equal to 0 to 6 minus 2x. And x will vary from 0 to which point? 3. X will vary from 0 to 3. So this is 2y, 3 minus x. First integrating with respect to y, then integrating with respect to x. So when we integrate with respect to y, keeping x constant, integrating to y, we get y square. So 3 minus x is constant. So we get y square, applying limits from 0 to 6 minus 2x. So you get 0 to 3, 3 minus x times. The 6 minus 2x is again 3 minus x. 2 into 3 minus x. So I get 2 square into 3 minus x, the whole square dx. So I get 4 times integral 0 to 3, 3 minus x, the whole cube. So I get 4 times 3 minus x whole power 4 by minus 4, 0 to 3. So 4 cancels. Substitute 0 minus 3 power 4 upon minus 1. So answer is 3 power 4, which is 81. So integral f dot n ds over the surface is 81. So problem, so it is little involved. The concept of okay applying is straightforward, but when you actually practically apply, first step we had to find the normal of the surface. Then we have to do f dot the normal. Then after that we had along ds we cannot integrate, so we have to project it in a plane. So best is xy plane. So what did we do? We took the projection of ds vector along the z axis. So the magnitude will be in the xy plane. So this equal to dx dy. The projection of ds along k is dx dy. So we get this. And from there, we just substituted n cap because in the plane it is constant. So we get this relation and we have integrated. Okay. And then it converted to a double integral, a function of several variables. And then we substituted the limits and then carried out the integral. So surface integral, little we need to be a little thoughtful to do that. Now let us look at the second question on surface integral. Okay, now if f is equal to z square I cap plus x square j cap minus y square z k cap, and S is the surface of the cylinder. and S is the surface of the cylinder. X square plus Y square is equal to 16. In the first octant, between Z equal to 0 and Z equal to 5, right? Then evaluate integral f dot n ds. Okay, so here is a trick. Let me see if I can draw a three-dimensional object. So yeah, this is a cylinder. Now, we will draw a three-dimensional axis. I'll just show that. First, the base, the unseen base of the cylinder. Okay, this is the unseen base. Now we will have a axis starting from the center. So this is x-axis, y-axis, and according to right hand thumb rule, the z-axis will be up. Okay, now this passes through the center. It passes through the center here. Okay, now at this z-axis, this is the plane z equal to 0, and this is the plane where z equal to 5. Now, interestingly, our surface is a cylinder. Now, what is useful to us is using cylindrical coordinates. using cylindrical coordinates. So R or polar coordinates R theta Z. R theta Z. Polar coordinates is R theta. When you include Z, this is cylindrical coordinates. It gives around a circle. At any given point in space, R represents the distance from the Z axis. All right. Theta is, the angle, made with the x axis. All right. R is the distance and Z is the point on the top. So R theta Z. R theta Z. So now let us find the equation of the normal. Equation of to the normal to the surface, or finding normal to the surface. Now normal is not having any along any z axis. It is only about x axis. So you have x square plus y square is equal to 16. Okay. Now, how to find normal to the surface? We know that the gradient. So if f of x comma y comma z is equal to some constant c, then grad f represents normal. This we know, right? Therefore, gradient of f here is 2x I cap plus 2y j cap. If this is treated as f of x comma y comma z. So this is the normal to the surface. So unit normal will be gradient of f small f by modulus of gradient of small f. We have done problems already on this. So we get 2xi plus 2yj upon under root of 4x square plus 4y square. So you get xi plus yj by x square plus y square under root. Now x square plus y square is equal to 16. When you substitute, we get this. Unit normal is xi plus yj upon 4. This is the unit normal. Now, we need to find f dot n and also we need to find ds. So, okay. Now, ds, so this unit normal. So first let us do f dot n. F dot n. F is given to be z square I plus x square j minus y square zk. So z square I plus x square j minus y square zk times xi plus yj upon 4. This gives us z square x upon 4 plus x square y upon 4. 1 by 4 times z square x plus x square y. This is f dot n. Now to find ds, now how to find ds? So if you look at this element is ds. Now with the x-axis, it makes an angle theta in the direction of x. Okay. And this is of course dz. Now this length, this particular length, see, this will be d theta. Now this particular length will be r d theta. And this particular height here will be dz. Okay. So this shaded region here, which is ds, the shaded area is r d theta dz. Okay, r d theta dz ds. So to find ds from the figure, ds is r d theta dz, and r is 4. The radius is 4. So 4 d theta dz. So this is ds. So now, because of polar coordinates, we can write x as in cylindrical coordinates. These are polar coordinates in 3 dimension is cylindrical coordinates. So in cylindrical coordinates, x is equal to r cos theta, y is equal to r sin theta, and z axis remains the same. The polar conversion doesn't take place. So now in this particular case, because we are doing a surface, r is fixed 4. So r is fixed for the given surface. So for the given surface, this is fixed. So now we have to integrate. So integral f dot n ds is integral okay 1/4 z square x plus x square y times ds is 4 d theta dz, 4 d theta dz. Now we will apply the limits of integrals. So 1/4 and 4 cancels. Eliminate that. Now z square remains as it is. You have x as 4 cos theta plus x square is 16 cos square theta times 4 sin theta into d theta dz. Theta will vary because it's a surface 0 to 2 pi, and z varies from 0 to 5 given the limits. So we can integrate whichever way we want. Oh, I'm sorry. He says in the first octant. So in the first octant means it is only in this coordinate. So theta will vary from 0 to pi by 2. First octant 0 to pi by 2. So now let us integrate. Leaving z, let us integrate, treating z as constant. Integral of cos theta is sine theta. So 4 sine theta. Applying the limits from 0 to pi by 2 plus 16 into 4 is 64. Now, derivative of cos theta is minus sine theta. So we just need to evaluate integral cos square theta sine theta. Of course, we can directly use Wally's formula. It is easier. Cos square theta sine theta. You will get 1 into 1 upon 2 plus 1, 3 into 1. So 1 upon 3 directly. I don't have to do anything now. Dz. So this is using Wally's formula. So z is equal to 0 to 5. I have 4z square plus 64 upon 3 dz. This is 4z cube upon 3 plus 64 upon 3 times z from 0 to 5. So we get 4 into 5 cube upon 3 plus 64 into 5 upon 3. So you get 4 into 125, that is 500 upon 3. Okay. 64 into 5 upon 3. So this is 500 plus 6 5 30, 320 upon 3. So you get 820 upon 3. $820 upon 3. This is the value. So this is the required result. So here, again, I'll review a little bit. So here it was a cylindrical surface. Here it was a three-dimensional plane, the area of integration, surface integral. Here it was a cylindrical surface. And function was given, and we need to find the dot product and the area integral. So because it's a cylindrical surface, the easy method to do is use the cylindrical coordinates r theta z. So r theta is along the xy plane, the polar coordinates, and z is in the z direction. So this is the surface x square plus y square equal to 16. This circle extended from z equal to 0 to z equal to 5. So we get this surface. Okay. So first, what did we do? We found the normal to this surface. How did we find the normal? Because we know that the gradient grad f is normal to the surface. This in the very first class of gradients, we did this. So grad f by mod grad f, or this will give us the normal, unit normal. So once we found the unit normal, we found n cap. So we can do f dot n cap. That is done. F dot n cap we did. We found an expression. Then we have to find ds. Now ds, because how will we integrate? We have to integrate with respect to the coordinates along the surface. So best integral is using polar coordinates, the cylindrical coordinates. So the ds, we found that this is r d theta and this is dz. So r d theta dz will give us the surface area of the element, infinitesimal element, ds. So ds is r d theta dz. So we have used that r d theta dz. R is constant here, 4 units radius, x square plus y square equal to 16 means r is 4. Now 4 d theta dz. Now we substitute cylindrical coordinates. So we do f dot and ds. Within this, we replace x, y, and z using cylindrical coordinates, and dz by 4 d theta dz. When we substitute cylindrical coordinates and then apply limits, because we want the first octant, theta varies from 0 to pi by 2, and from the bottom surface to top surface, 0 to 5. So theta and z, we apply, and then we solve. First, we integrate with respect to theta, keeping z constant. Then we integrate with respect to z. And this is how we get. So there's this surface integral. Okay. Another one. Sphere will be a much difficult one. There is a problem on sphere. Okay, I'll do it. Because we have done along a plane, we have done along a cylindrical surface, then around a spherical surface. So evaluate surface integral a dot n cap ds, where a is yz I cap plus zx j cap plus xy k cap, and s is the part of the sphere x square plus y square plus z square is equal to 9 in the first octant. Okay. I need to show a figure for this. Let me see if I can get it. A figure will help you. Huh. I think this. Okay. Another figure is there which will help better. So in spherical coordinates, at any point, r is the distance from the origin. Okay, r is distance from the origin, and uh, okay, d phi here. Okay, here it is theta. This is r distance. This is the direction of r. This is the direction of theta with the x-axis, and this is azimuthal angle from the uh, vertical axis. So r d theta dz. This is so. So the element here in this direction, if we go, you get r d phi, because from here to here we are taking an element. You see here a volume element. Now along the r direction, this will be dr. So see, very clearly he has pointed out this arrow. This arrow is r d phi, and this arrow, which is this length basically, all right, is r sine phi, r sine phi. uh, okay, he has given your sine phi. Yeah, r sine phi d theta, r sine phi d theta. This is a better figure. I'll delete this one. So this is r d theta. How did we get r sine phi here? Okay. Of course, if you go back to the Jacobians that we did, okay, and we found the converting the volume to just change of variables. Yeah, the volume integral we converted r sine theta dr d theta d phi. That time Here, this is a figure. Okay, this is Z, this is X, this is Y, this is phi, this is D phi. Okay, so now this is R, this point is R. Now, when I do a projection, this projection is R sine theta, because this is theta. This is theta. So this length, this particular length is R sine theta. On XY plane, this length is, this particular length is R sine theta. Okay, here, this is showing R sine theta. Now, R sine theta is this radius. R is the projection of radius in space. I take that projection on the XY plane, so I get R sine theta. Now, R sine theta into d phi will be this R sine theta d phi, this length. So that's what we got. This surface, the top surface here, is R sine theta. Okay, is not, this top surface is R sine theta d phi, and this angle, let's go back here. Yeah. Okay, in this figure, theta and phi are interchanged, doesn't matter. So this was R. So you will get R sine phi theta, d theta, and R d phi. So this is just reverse in that particular figure. Maybe we should just use that particular figure. That will be much safer. Okay. So now, how to find n gap? This the solution. This is the surface. This particular thing is the surface. Okay. So this particular surface will have, now let us do the calculation. N cap will be gradient f by modulus of gradient f. Gradient of x square plus y square plus z square equal to 9. So you get 2x I plus 2yj plus 2zk upon 2 root of x square plus y square plus z square, which is 3. So we get xi plus yj plus zk upon 3. This is the n cap. Now a dot n cap. Now a is given to be yz I cap plus zx j cap plus xy k cap dot xi plus yj plus zk upon 3. Okay. So we get xyz upon 3 plus xyz upon 3 plus xyz upon 3. Therefore, a dot n cap is xyz. So a dot n cap we found. Now we have to find ds. So in spherical coordinates, ds is this one. ds along the radial direction. The figure is not correctly pointed out, but it's at the bottom here along the radial direction here. R square sine theta d theta d phi. R square sine theta d theta d phi. Okay. So only dr is missing from that Jacobian change of multivariate theorem here. From the Jacobian, the volume integral, you have r square sine theta dr d theta d phi. Only dr is the missing term. Okay. So dr is what is different, because along the thickness, radial thickness, we are not considering, because we are considering the surface. Okay. So in spherical coordinates, this is this. So now integral, therefore, now spherical coordinates, we have to write x is r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta. So I is integral over the surface of x, y, z times r square sine theta d phi d theta. Now d phi is this angle in the xy plane. So because we are restricting to first octant, so phi varies from 0 to pi by 2. And then this theta in the, up to the z coordinate. So from 0 to pi by 2. Theta also varies from 0 to pi by 2. Now we replace x. Now r is 4. And r is 3 throughout, because it's a sphere of radius 3. So r is 3. So x we can write as 3 sine theta cos phi times y, 3 sine theta sine phi, z is 3 cos theta times r square, 3 square sine theta d phi d theta. So we have integral theta varies from 0 to pi by 2. So if we remove all, now this is 3, 3, 3, 3 power 5 sine square theta sine cube theta cos theta. Okay, then we have cos phi sine phi d phi or d phi d theta. So whichever one we want to do first, we can integrate. Sorry. So let's first integrate with respect to phi. We can keep using Wallis formula, most easy. 3 power 5 theta equal to 0 to pi by 2. Whenever 0 to pi by 2, Wallis formula is the most easy. So Wallis formula for this, if we do, we get 1 into 1 by 1 plus 1, 2. So 1 upon 2, or direct integration. Now Wallis formula for this, if we do, we'll get 3 minus 1 is 2 into 1 by 4. 3 plus 1, 4 into 2. So this is Wallis formula. So we'll get upon 4. So 3, oh, and 1 by 2 is also there. So 3 power 5 into 1 by 4 into 1 by 2. So we get 3 power 5 upon 8. 243 upon 8. 243 upon 8. So this is the surface integral. Okay. So tomorrow we have 3 important theorems to do. We'll stop now here. 3 very important theorems: Green's theorem and Stokes theorem, basically, and Gauss divergence theorem. So these 3 theorems we will do, and I'll just show you. Let me see if I can show you how many problems you get on this. Let me just check. Yeah, I'm just showing you. Oh, not this. Yeah. So here you see questions on vector integration. These are questions on line integrals. This a period of 10 years. We get line integrals. The problems that we'll do problems tomorrow after we finish Green theorem and Stokes theorem. And then we see surface integral, not much, but surface integral, there's a connection of line integral and surface integral. That is why. So on these Green's theorem, Stokes theorem, and divergence theorem, we have plenty of questions. Okay. So many questions come. And in the last 5 years, there are many more. I'm adding that. All right. So we will discuss these things tomorrow, and we'll do some practice problems also. Okay, so this part, what we learned in the last two classes, the vector calculus part, because of the comprehension, we have to visualize in 3 dimension and it's a vector. So we need a lot of practice for this. So last week I shared a practice sheet. So you please do that. I'm doing problems in class and you can look into practice sheet. Two very good basic books for engineering maths, the textbooks where you can get all kinds of solutions is, one is of course B.S. Grewal, Higher Engineering Mathematics. Other one which I've seen, and it has a very good compilation of things, is Advanced Engineering Mathematics by H.C. Taneja. These are the books which will give you all the basics for you. All right, from problem solving point of view, if you have any doubts, and some of these books are available online for free. Free PDFs are available. You can download and cross refer whenever you have any difficulty. All right, so we will stop for now.